So here is the video walkthrough for our practice test B on covalent ionic metallic bonds and whacking in some mole calculations just for good measure. This question is question 1. Ammonia is a toxic gas with a multitude of uses. It is formed by reacting nitrogen gas and hydrogen gas in the presence of a nickel-based catalyst. Balance the chemical equation below to show the production of ammonia. So, balancing chemical equations. We need to make sure that we have the same number of particles on both sides of our reaction as our reactants and products. Here we can see we've got 2 nitrogens, we've only got 1 nitrogen there, so we need a 2 as a prefix here, as a coefficient, sorry. We've got 2 nitrogen, that's good. Now we've got 6 hydrogens, so I need a 3 here, and therefore this is now going to be balanced because I've got 2 nitrogens on both sides. I've got 6 hydrogens on both sides. Life's good. It's all balanced. It's all about just going through it systematically and saying how many of each do I need to make it balance. Question number B. Draw the valence structure showing all bonding and non-bonding pairs for each compound involved in this process. So here we have nitrogen. Again, valence structure is about thinking, how does this come together? Nitrogen's in group 5, so therefore it's got 5 electrons in the outside shell. That gives me a bond of a triple bond because each of these will be bonded to another nitrogen. Hydrogen, this is our Lewis dot structure for hydrogen. Therefore, we're just simply going to be having hydrogen bonded to hydrogen. No lone pairs because hydrogen's a bit of a small guy. This one here, now we have our nitrogen with 5 electrons, our hydrogen with 1 electron, so therefore we can see that the unpaired electrons will marry up here, and you're going to end up with a lone pair of electrons and 3 bonding pairs of electrons here. Important to note that you're showing all bonding and non-bonding pairs of electrons, not just the ones that are the bonds. Question C. All 3 substances above are gases. However, each have a unique boiling point. Which compound would you expect to have the highest boiling point and justify your response? Boiling point is all to do with forces and intermolecular forces. So let's look at these molecules and work out whether they're polar or non-polar because forces come from polarity. So therefore, this guy here is going to be non-polar because he's symmetrical. This guy here is non-polar because he's symmetrical. This guy here is going to be polar because he is not symmetrical. You can see therefore there's a difference in charge here. So that by just looking at that, you can see that NH3 is a polar substance. So therefore, we'll have a higher boiling point than N2 or H2, which are non-polar. But again, because I want to say this is to do with forces, I'm going to then describe the forces. So NH2 equals hydrogen bonds, which are stronger than the dispersion forces in H2 or N2. And that's going through both the polarity of our molecules and then going into the intermolecular forces of those molecules. And you need to have both of those there. You've got 3 marks. 1 for identifying the thing that's going to have the highest boiling point, 2 for talking about the polarity, and 3 for talking about the forces involved within these molecules. Part D, a factory uses 1.5 tonnes of nitrogen gas every hour. So therefore that's that. Calculate the amount of nitrogen gas. So therefore number of moles of nitrogen gas equals M over MR. Now I've got tonnes. 1 tonne is 10 to the power of 6 grams. So it's going to be 1.5 times 10 to the power of 6 divided by my molar mass of nitrogen, which will be 28. So therefore you go here, turn it on, 1.5 times 10 to the power of 6 equals that number. Divide that by 28. And that gives me 53,571 mole. Deduce the amount of ammonia produced in this process, number of moles of ammonia. All right, what's the link between here? I've got 2 nitrogens and I've only got 1 nitrogen here. So that means that my nitrogens here, I could make 2 ammonias. So it's going to be 2 times the number of moles of nitrogen, because I've got clearly 2 nitrogens. That would make 2 lots of ammonia. For every one of these, I could produce 2 of those based on the ammonia. So it's going to be 2 times 53571. Take this guy and go times by 2. Gives me 107. 142. No, 143, because look at this, I've got to round it up. So therefore that's going to be mole of ammonia. Calculate the mass in kilograms of ammonia. Mass of ammonia equals, what's it going to be called? Number of moles times molar mass is 107,143 times by my molar mass of this, which is 14 plus 3 is 17. So that's going to be times by 17. Gives me 1,821,429. That's grams. So how many kilograms is that? That's going to be 1,821 kilograms, because it's divided by 1,000. You can't even see that. There it is there. Okay, so that's our mass of ammonia. And here's for a bonus question, the mass of hydrogen required for this reaction. Well, what's interesting, you can do this a number of ways. You can do it lots of mole calculation ways. So I could look at, if this is the number of mole of ammonia, I could times that by 3 and then times that by the mass of hydrogen. Or I could say, well, if my ammonia is 1,821 kilograms, my nitrogen was 1,500 kilograms, my hydrogen must be the difference between those two. So therefore, I'll take this and go 1,821, take away 1,500, it would be 321 kilograms, because I know that the mass of my ammonia must be equal to the nitrogen plus the hydrogen. It's a bonus mark if you want to look at that, and just good thinking about how chemistry works in terms of masses and moles and stuff. That's the end of question 1 done.